Hi, I'm Ryan Baker, and this is Big Day in Education. Welcome to video 4 of Relationship Mining Week. In this lecture, we're going to talk about sequential pattern mining. Sequential pattern mining is a close variant on association rule mining, which we discussed last class, where you try to automatically find if-then rules within the dataset. In sequential pattern mining, you do the same thing, but you're trying to automatically find temporal patterns, patterns occurring over time within the dataset. So the association rule mining example, if person X buys diapers, person X buys beer, and the purchases occur at the same time. In the sequential pattern mining example, if person X takes intro stats now, then person X takes advanced data mining in a later semester. Conclusion, recommend advanced data mining to students who've previously taken intro stats. Maybe they'll find it interesting, like some of their classmates did. Doesn't matter if they take other courses in between, by the way. Sequential pattern mining can look at immediate relationships or relationships spread out over time. Sequential pattern mining has been used a lot in educational data, and one example I particularly like is work by Jen Saborin, Brad Mott, and James Lester, where they found that learners in virtual environments have different sequences of behavior depending on their degree of self-regulated learning. For example, students with high self-regulated learning tend to gather information and then immediately record it carefully, whereas students with low self-regulated learning tend to gather more information without pausing to record it. Now, there's some different constraints for sequential pattern mining than for association rule mining. For one thing, if-then elements don't need to occur in the same data point. Instead, if-then elements need to involve the same student or other organizing variable like teacher or school, and if elements can be within a certain time window of each other. The then element time should be within a certain window after the if times. So if, then. So in sequential pattern mining, we find all the subsequences in the data with high support. And support is calculated as the number of sequences that contain the subsequence divided by the total number of sequences. You may recall this from last time. And then we use the GSP, Generalized Sequential Pattern Algorithm. There's other algorithms too, but this is the classic one. You may notice the name Agrawal again. In this approach, data is transformed from individual actions to sequences by user. So for example, we say Bob has gaming and board, then he has off-task and board, then he has on-task and board, and so on. And we can also perhaps include time that may be relevant. We may not just want to look at number of sequence items apart, actions are for the if-then rules. We may want to look at time. Maybe we want to look at rules that occur within a 1 minute time window, or 20 seconds, or 1 year. We take the whole set of sequences of length 1, which may include ANDed combinations occurring at the same time. For this, we only care about patterns that occur at a given time. We find which sequences of length 1 have support over a pre-chosen threshold. Then we compose potential sequences out of pairs of sequence of length 1 with acceptable support. So for example, if both AB and CD have acceptable support, then we could look at if AB now, CD later, and if CD now, AB later. Then we find which sequences of length 2 that we've created have support over our pre-chosen threshold. And then we compose potential sequences of triplets out of sequences of length 1 and 2 with acceptable support, and so on and so forth. We continue until we don't have any new sequences that are supported above the pre-chosen threshold. So let's try actually executing the GPS algorithm, and we'll set min support to be 20%. Let's say we have 4 students who over time have a certain pattern of behaviors which we're going to just label with letters for the time being. You could think of like A as gaming a system, and B is off task, and maybe C is bored, sort of so on. So we start out with A, B, C, D, E, and F. Now does AC have support over 20%? Let's look. Well, Chuck has A and then C, and here's another A and then C for Chuck, and here's another A and C for Chuck, and now we're going to go to the next A. We keep that next A. You notice we don't in the ABC count A to C because A and C are occurring at the same time, and that's not a temporal pattern. So we're looking at the second A to the third C, and then the second A to the last C, and the third A to the last C, and so on. We can kind of go on looking for A's and C's across Darlene, across Egoberto, across Francine. What we find is that we see AC in 14 cases out of 40, which is 35%. So AC has enough support to keep. Turns out that AD and AE also have enough support to keep. What about triplets? We can now try combining AC, AD, and AE with A, B, C, D, and F. And we get AAD. Let's look at AAD. Well, here's an AAD. Here's another one. Here's another one. Here's another one. And so on and so forth. It turns out we also have enough support for AAE and ADE. Now we can go from these things, AC, AD, AE, AAD, AAE, ADE, to create A to C, A to D, A to E, A to AD, A to AE, and AD to A.
Now, GPS is not the only way you can do this. There's other algorithms like free span and prefix span, which select subsets of data to search within. There's SPADE, which does a depth first rather than a breadth first search. These are faster, but they're the same basic idea as in GPS, so I won't go into detail.
A variant on sequential pattern mining that I personally find quite useful is differential sequence mining, which compares the support for sequential patterns between two groups. For example, you might look at the different sequences that are characteristic of high-performing students versus low-performing students, and when you compare these two groups, you can try to find the patterns that are much more common in one group than the other.
Now, a recent trend in this area is trying to discover concise pattern descriptions. Some contemporary algorithms attempt to find groups of patterns that can be described more concisely. And there's a nice review of this in Fournier-Vigier et al. 2017.
So, it's worth mentioning briefly, by the way, process mining, which is an algorithm related to this. In process mining, rather than just finding small local patterns, like we've talked about in this lecture, it tries to find overarching processes that occur over the course of a set of events, or it tries to find discrepancies in approved processes. So for example, do students' self-regulatory processes over time match the theoretical models of self-regulated learning? So that's it for sequential pattern mining. Thank you very much for coming today. In our next lecture, we're going to talk about network analysis, which is a completely different method for studying relationships within data. I'm Ryan Baker. This is Big Data Education. Thank you very much.